Now that we've got power rule down under our belt, we want to go over combinations of functions. So what happens if I have multiplication of two functions, if I have division of functions? So in this section, we're going to learn about two more types of rules, and then we're also going to learn about how to take higher order derivatives. So what does it mean for a second derivative, a third derivative? How many times can I keep going? So we're going to begin first by going over the product rule. So how do I take a derivative if I'm multiplying two functions? The one thing that is super common is it's really tempting to say, if I take the derivative of one function times the other, I'm just going to differentiate each of them separately. But this is no good. We do not want to do that. So this is completely wrong. What I'm going to do is show you a function but this is completely wrong. We actually can't do that. To show you why it's a problem, I'm going to consider two simpler functions. So I'm going to let f of x be just x and g of x be x squared. So if I take the product of these two, it would be x times x squared or just x cubed. So if I want to take the derivative of their product, the derivative of x cubed is 3x squared. But instead, if I try to differentiate these separately, the derivative of just x would be 1. The derivative of x squared is going to be 2x. So the product of the derivatives is 1 times 2x. It's 2x, not the same as the true derivative. So here, the derivative of each separately multiplied together is 2x, which is not the same as 3x squared, which is our actual derivative of the product of two functions. Now, that being said, I do care about the individual derivatives. I am going to have to figure out what the derivative of one function is and what the derivative of the other is, but there's other stuff we have to do. So this is where our product rule comes into play. If we have two differentiable functions, f and g, if I want to differentiate their product, what we do is we keep the first function, differentiate the second. Add to that now the derivative of the first, keeping the second. So pretty much you flip-flop. Keep alone, differentiate. Then you reverse. Differentiate, keep alone. This notation I know can get a little bit confusing, so I'm also going to give it with that prime notation, which represents our derivative. So we keep f, differentiate g, differentiate f, keep g. Okay. So I am going to go through the proof of this, and I'm going to do the same when we get to quotient rule, which is for the division of two functions, because you're at a point now that we do want to see where things come from if it's not terribly tedious to do. So where it seems appropriate, I will go through that proof of it. And all it does is it boils down to the definition of a derivative. So we're going to go ahead and look at that limit definition. If I look at the derivative of this function, it is the limit as h goes to 0 of that difference quotient. So I would evaluate this at x plus h, subtract the function itself, and divide by h. So I would evaluate this at x plus h, subtract the function itself, divide by h. So that is our difference quotient applied to f times g. The technique we have is I want to see two different derivatives pop up, so I'm actually going to add and subtract something to help us out. So right here in the middle, I'm going to keep that first term alone. I'm going to subtract this quantity, f of x plus h times g of x. But I can't change this, so I'm going to add it back in to make it so these two would cancel each other out. And then I've got my final term here, and this whole thing is divided by h. So if you notice, in this first piece, they both have this quantity f of x plus h. In the second piece, they both have this g of x. So what I'm going to do is split this as two limits. Keep the first two together, keep those second two together, okay? And now we're gonna factor out those common pieces. So I'm gonna take this quantity out of my first one. I'm gonna take g of x out of my second one. So that gives me the limit as h goes to 0 of f of x plus h. And what's left over then is g of x plus h minus g of x over h. Over here, I pop the g of x, and I'm going to pop it on the right-hand side. And I'm left with this quantity f of x plus h minus f of x over h. Okay? Now we're going to use our limit laws. So I've got the product of two things that do both deal with h. So my limit laws tell me I can take the limit of each individually. And then over here, g of x has nothing to do with this limit itself. So we'll go ahead and just pop that outside of the limit. Okay. Now in this first piece, I have 0 issues plugging in h as 0. That just goes to f of x plus 0. And this quantity here is exactly my formal definition for the derivative of g. So that is representing g prime of x. Likewise, this is my formal definition for the derivative of f. So that's f prime of x times that g of x. And then in here, x plus 0 is just x. So we get exactly this product rule. So let's get a little bit of practice actually trying to go through and differentiating the product of two functions. We're going to start with this function y equals 3x plus 1 over the square root of x. That is being multiplied by sine of x. So to take derivatives, I want to rewrite that 1 over square root of x. That's x to the negative 1/2. So what my product rule tells me is if I want the derivative of this function, I'm going to keep this first piece, and then I want to multiply it by the derivative of this second piece. Then I'm basically going to rewrite exactly the same thing, and that derivative switches to the first piece instead. So I can't emphasize enough, it's really important that you practice writing everything out. Don't jump into immediately taking the derivative, because when you have really complicated functions, it's going to be hard for you to notice if you made a mistake, and it's also going to be really hard to keep track of stuff, especially when we go through the chain rule. So go through and actually write it out with that prime to indicate where you need to take a derivative. Because now it's a little bit easier to see. Derivative of sine of x, we learned last time, is cosine of x. And then the derivative of this polynomial, derivative of 3x is 3. Derivative of x to the negative 1/2. So remember, we bring that power down, and then we decrease the power by 1. And then that's being multiplied by sine of x. Okay. So now I'm at a point, I've taken all the derivatives. I'm just going to clean it up so it looks a little bit nicer. The x to the negative 1/2 is that 1 over square root of x. This is being multiplied by cosine of x. And then here, this is 3 minus 1 over, you have 2, and this becomes x to the negative 3/2 times sine of x. Okay. And you could instead move this down here. This is x to the 3/2 to make it positive if you want to, but it's not necessary. So you could leave that one in that form. Okay. All right, let's try a second one. Let's take the derivative of cosine times sine. So again, the product of two functions, I'm going to keep the first, multiply by the derivative of the second, add to that the second, or the first, add to that the derivative of the first times the second. So the derivative of sine is just cosine. Derivative of cosine is negative sine. So simplifying, this is going to be cosine squared of x minus sine squared of x. Okay, so let's go through our next rule, which is our quotient rule, and I'm going to go through the proof of this as well. Definitely more complicated if I want to take the derivative of one function divided by another. It's going to look messy, but there's a nice mnemonic that can help you really remember it. We go ahead and get the low function. We multiply that by the derivative of the top or numerator function. Subtract the high function multiplied by the derivative of the denominator. And this whole thing is divided by the denominator squared. So in terms of the prime notation, it looks like this. I take the denominator, derivative of the numerator, minus the numerator, derivative of the denominator, all divided by the denominator squared. The mnemonic is way easier. This is something I learned in high school, and it has stayed with me since I was 17 years old at that point. It's low, D high, minus high, D low, all over low, low. So that might be something quicker for you to go through your head, and every time I take a derivative in a video, I'm going to keep bringing up that mnemonic over and over and over again. Okay? So we are going to go through the proof of this. It's really similar to the last one, but again, I want to get you familiarized with just manipulating and seeing where things come from. It boils down to that limit definition, so I have to apply that difference quotient to this particular function. So we get the function evaluated at x plus h minus the function divided by h. And again, what I'm going to do is combine these first to a single fraction. So I want to get a common denominator to those. This divided by h looks disgusting right now. So what I'm going to actually do is put a 1 over h on the outside. Dividing by h is like multiplying by 1 over h. So I've got this numerator. I want to make it a common denominator. So I need to multiply this first piece by g of x. So we're going to multiply by g of x over g of x. This piece needs a g of x plus h in the bottom, so top and bottom get multiplied by that. So it really creates one giant fraction. My numerator would be g of x times f of x plus h minus this. And then my common denominator is going to be g of x plus h times g of x. And this quantity gets multiplied by 1 over h. Now, same as before, I'm going to add and subtract some quantity to really help me out. So what I'm going to do is keep this piece. I want to subtract f of x times g of x. But since I'm subtracting, I need to balance and add this exact quantity in. So my numerator becomes this, and it's all over g of x plus h times g of x. And then this 1 over h is chilling off here to the side for now. Okay. Now within this, from the first two pieces, I have a g of x in common. From the next two pieces, I have f of x in common. So we're going to go ahead and factor those two things out. So this is the limit as h goes to 0. I'm taking that g of x out, and I'm left with f of x plus h minus f of x. Then I'm going to take this f of x out. And what we're left with is g of x plus h minus g of x. And what we're left with is g of x minus g of x plus h. And then this whole thing is divided by g of x plus h. And then off to the side, we also have that 1 over h. Okay. And now I'm going to rearrange again. If I'm timesing by 1 over h, you could put the h down here in the denominator, or you can make this numerator completely over h. And so that's the one I'm going to do. This is the limit as h goes to 0. We've got that numerator divided by h, and that whole thing is divided by this g of x plus h times g of x. So you can see in the limit, this is going to go to g of x times g of x. It's going to be g of x squared. Okay. Now I can take each individual piece divided by h, this piece divided by h, to give me basically two fractions within the numerator. So I've got g of x, and then we're going to take that piece and divide it by h, subtract f of x, take that piece divided by h, and then still exactly that same denominator. And so when we take this limit, this is exactly our difference quotient for f, our difference quotient for g. Those turn into f prime and g prime respectively. So that numerator is g of x, f prime of x, minus f of x, g prime of x, and the denominator goes to g of x times g of x. So this is where our difference quotient comes, or our So this is where our quotient rule comes from. Okay. So now that we've got the quotient rule, let's try some examples. Let's differentiate the function f of t, which is sine of t over sine of t. So we're going to use that nice mnemonic to help us out. To take this derivative, we do low d high minus high d low all over low low. So you get t times t, you just get that denominator squared. Okay. So you can see it's really important for us to sit here and go through and write everything out before taking a derivative. Because if you do it in your head, it's going to be easy to mess it up. And now I just need to take these derivatives. Derivative of sine is the cosine function. Derivative of t is just 1. So the derivative of this function is t cosine of t minus sine of t divided by t squared. Okay. Let's try a second example. We're going to have a polynomial over a polynomial. So applying our nice mnemonic again, which sounds a lot like yodeling, we get low D high minus high D low all over low low. So we get that denominator squared. So this is a prime example. If you tried to take derivatives in your head, that's a lot to keep track of. And it's very easy to mess up on a piece of paper, just a tiny constant, which will make your answer wrong. So we've got to take derivatives. Derivative of x plus 1 is 1 plus 0. So really just 1. Derivative of x cubed is 3x squared. Derivative of x is 1. Derivative of 2 is 0. Okay. Now, realistically, you could leave the answer like this, but because we're about to talk of higher order derivatives, it's going to be really useful to clean this up a bit. So multiplied by 1 does nothing. I want to distribute that minus sign, but I do have to FOIL these out first. So if I go through and look at my first pieces, that will give us 3x to the third. The outside is x. The inside is 3x squared. So I'm going to just put that first. And then the last term is 1. And then it's divided by this denominator squared. Okay. Now we can condense things, so we'll distribute that minus sign, but luckily something nice happens. We have a positive x when we distribute that to this. So we have a positive x. We're going to distribute this minus sign to this positive x. These two end up canceling each other out. Okay. Grouping our other like pieces, we've got x cubed. It'll be minus 3x squared. So that will be negative 2x cubed. Grouping our other pieces, this is x cubed minus 3x cubed. So in total, that will be negative 2x cubed. I don't have any other x squared terms up here, so when that minus distributes, it's just minus 3x squared. We've got minus 2, distribute that out, becomes minus 1. To give us minus 3 as our constant. And then we've got x cubed plus x minus 2 squared. Okay. So don't be afraid to take more steps than you need to. If you needed to distribute that minus out before combining, absolutely do what you feel comfortable with. Okay. Now that we've got this quotient rule under our belt as well, we're going to go back to the rest of those trig functions. So we saw the derivatives of sine and cosine using those special limits that we talked about. We're going to start by just working with tangent of x because the others are going to be super similar. If I want to differentiate tangent of x, remember it's just sine over cosine. So really, we can just use quotient rule. The derivative of this function is we do quotient rule, low d high, high d low, all over low d low. So we get the low function, d high minus high, d low, all over low low. Well, derivative of sine is cosine. Derivative of cosine is negative sine, all over cosine squared. So cosine times cosine is cosine squared, minus minus gives us a plus, sine squared, all over cosine squared. And if you remember your Pythagorean identity, cosine squared of x plus sine squared of x is always going to equal 1. So that numerator becomes 1 over cosine squared. And that is just secant squared. So ultimately, the derivative of tangent of x is secant squared of x. Okay. For all of those remaining trig functions, you can really do exactly the same thing because secant is 1 over cosine. Go through applying that quotient rule. You're going to find out the derivative of secant is secant tangent. Derivative of cotangent is a lot like tangent. It's negative cosecant squared instead. And then likewise, secant and cosecant are similar. So they're going to be opposite in signs, but the same idea. Cosecant, cotangent go together. So these are all of our trig function derivatives. All right. So if you want to go through, you can work through some of them yourselves, but you can easily kind of recognize patterns in these things to help you memorize the derivatives. So let's try one simple example. Let's differentiate 2 over x minus 7 secant of x. Remember, x in the bottom is the same thing as x to the negative 1. So if I want to differentiate this, we apply that power rule. So the negative 1 comes down. The powers decrease by 1. Derivative of secant of x is secant of x tangent of x. So ultimately, this derivative is negative 2 divided by x squared minus 7 secant of x tangent of x. Okay. And then you can apply these with all of the other rules as well. So the very last thing we're going to talk about in this section is higher order derivatives. If you even look at this last example, I can keep going. I can take the derivative of this now because I'm just going to use power rule here, and I'd have to use quotient rule here. So I can take the derivative of this again. It would just be power rule for this first piece, and I'd have to use product rule here. That's okay, I could do that. And in turn, it would end up with another function. So if you have a differentiable function, its derivative is also a function, which you probably can differentiate again. So for example, if I have this nice polynomial, x cubed plus 2x squared minus 7x plus 4, if I take its derivative, it would be 3x squared. If I bring the 2 down here, it would give me 4x minus 7, which that can be differentiated again. In terms of the function itself, the first derivative talks about the slope of the tangent line or the rate of change of our function. If I take a second derivative, it tells us the rate of change of the first, so it's telling us the rate of change of the slope of the tangent line. So kind of as an idea, you're starting with some function f. If you take that first derivative, it's the rate of change of that function, which geometrically is giving you the slope of the tangent line. When you take the second derivative, it gives you the rate of change of the function above it. So it's giving us the rate of change of f, which ultimately is giving us the rate of change of the slope of our tangent lines. Okay. Notationally, we use this second derivative or two tick marks to represent taking a second derivative, because this would be absolutely awful to write to make a prime on a prime. So for this particular function, our first derivative is a polynomial. If I take that second derivative, it would be 6x plus 4. And this is something that I can still keep taking a derivative of. So in the same manner, if I want to take another derivative, it would be 3. So I'd use 3 tick marks. Third derivative would be 6. If I go to take 4 derivatives, derivative of 6 is 0. Pretty much after this point, the fifth derivative would be 0, sixth derivative 0. But you can kind of see this is hideous to write. Really, after 3, it gets super, super, super tedious and awful. So we have a different notation when we talk about these higher order derivatives than just the primes, just for simplicity and to keep things clean. So if I want to take the nth derivative, instead of writing n tick marks, we're going to use an n in parentheses to indicate that number. Or same thing, you can do y to the n, but the n has to be in parentheses. Because if you don't put parentheses, this would be like y to the third power. That's indicating something completely different, okay? In terms of the Leibniz notation, which is that d over dx, you would put the n in the locations attached to the d up top, and it's going to be with respect to the variable x n times, okay? So let's try one example. We're going to calculate 3 derivatives for a particular function x to the 1/5. So you've got to start with the first derivative. It's going to be a bunch of power rules. So we bring the power down. We decrease this power by 1. So 1/5 minus 1 would give us x to the negative 4/5. Then we keep going. The second derivative, we go ahead and bring that power down, and we decrease it by 1. So that'd be negative 4/5 minus 1, which gives us negative 4 over 25. This would be x to the negative 9 over 5. And again, the third derivative, 3 tick marks isn't so bad, but if you wanted to put a 3 in parentheses, that's perfectly fine too. So same thing, we bring the power down. So we bring this negative 9 over 5 down, and we decrease this by 1. So that would be 36 over 125. So minus minus makes it positive. Subtracting another 5 over 5 gives us x to the negative 14 over 5. Okay, and realistically, we can keep going with this, but we will stop here. Okay. So we've got 2 major tools now under our belt as well to be able to differentiate more and more and more functions. What we're going to do after this is talk about another derivative, which is the chain rule. And that's going to help us when we have functions inside of functions.